Okay. Today.
Vadim, sorry, P is not index of K.
Yeah. I'm sorry. First of all, I want to tell about Kappa equation in a little bit different way in order to. Well, I think it is an interesting way to look at it. I haven't seen it before. After that, I want to look at Kappa hierarchy as well, is a compatibility condition of following system of equation. I will introduce tool notation later. N L equals Ln plus L. Okay. This is the system of equation, and it is overdetermined, and the compatibility condition will be the whole hierarchy. After that, I want to write it down is one integral equation. After that, I want to show that from this one integral equation, I can obtain something called Hirota mu equation. This is a difference equation. It can be obtained from integral equation, and it is it could be shown that it is equivalent to it. I don't know, will I have a time for this, but it is one interesting. And this is for today. And next time I want to use this Hirota mu equation to obtain so-called almost intervenient matrices solution of Kappa. It is two matrices, for example, M and N, such that M and N equals L where rank L equals to 1. Well, it could be written just rank.
So you want to derive difference equation from continuous? From
yes.
PG?
Yes, today I want to get Hirota from integral equation. Yes, I want to show that this these three things are equivalent. Maybe I won't show that this is equivalent, but it could be done.
Okay, let's
okay, now in order not to bore everybody, let me introduce a interesting way to look at the Kappa equation. For example, we have just ordinary second order difference equation, just f for x plus ax f x plus bx f of x equal to 0. Okay, it could be written as if equals to 0. Now, if we have two functions f1, f2 solutions, we have x equals minus f1, f2, f1, f2 divided by Wronskian. Let me denote it by tau b of x equals f1, f2, f1, f2, the tau of x is f1, f2, f1 prime, f2 prime. This is the determinant.
You forget two primes in the expression for b of x.
B of x, yeah. Sorry. Well, okay, this is very simple, and it is material for the second year student, I guess. But now we want to f of x be dependent on the parameters. Call it x, y, and t. And for example, equals to with such dependence. Okay, now we want to go from a, which is a function of x, to a as a function of x, y, and t, b as a function of x, to b as a function of x, y, and t. Well, what do we want to do? We want the f, for example, equals to f plus d square f. This can be written as some order 4 differential polynomial on x, and it can be viewed, it should be equal to 0 since we have this equals to 0. And it can be the, so it should be equals to 0 when f equals to f1 of f1 and f2. I should maybe write it. So, so it could be written as some b2 acting on where is here is a second order differential polynomial. For example, b2 equals d square x plus alpha 2 d plus beta 2 x. Here and now on we have d equals dx. So in some places I could forget it, but if we have d without indices, it means that it's just dx. Now it can be viewed following way. We have d plus vd square equals to b2 as v. We could write it the following way. Rewrite it a y d plus b y plus d fourth plus a d third plus b d square equals 2. Okay, let me write it this way. D square plus alpha 2 d plus beta 2 times d square plus r d plus b. Now we see that these things are okay. Didn't defined. We should have an equation. Like when we open our bracket, we will have equation for up. This is d gamma a. This notation means from this derivatives, but well, like we have equations for coefficient of the first power of d or 0th power of d, but the coefficients of d fourth, d third, and d second are added, should determine alpha 2 and beta 2, and we see that, for example, this will give us d4. It's okay. Now d third should be this one plus this one, or when d square doesn't act on. So we should obtain something like d4 plus alpha 2 d third plus r d third. But we know that it should be just a d third, so we can get that alpha 2 is equals to 0. Okay, perfect. Now we want to determine b, and for example, d square, it should be like from the okay, let me write just plus b d square plus a 2ax d square when we this d acting on this commutating, it gives us this term, and another term when beta just with this, and this will be plus beta 2 d square. Okay, and we see that it should be equals just to b coefficient should be equals just b, so we have that b square equals minus 2ax. After that, if we compare coefficients, near first order and zeroth order, we obtain equations for D, and let me write it down. It's not so important, but probably I should write it down. This A gamma equals AXX minus 2AX 2BX B gamma equals BXX minus 2AXB. Okay, now we could do all the same for G, and we obtain some system of equations. Okay, and it is interesting that the system of equations are the same. It's just a first kappa equation. It is we could see just since we have like here we have this operator B2, it's nothing, just B2 of copy. It's minus 2FAX we could see that this condition we could just write it this way: the y v dt equals dt dy v. This will give us equation b2t minus b3 y equals to b2 b3, and we could find out the same way that this is operator is M or something. This B3 is also a kappa operator, and so.
Vadim, where you found this proof? This derivation?
Well, it's from this book of discrete integrable system. It's like a collection of different like articles, or I don't know, and this called a SATA how to call it, something like SATA approach to integrable system. I think it is a nice one.
It is.
They called it a SATA approach. And when I called my not Wronskian is tau function, it's because it is a tau function. It appears that here we see that AX is something we called U in kappa, and we know that since we have the definition are the same, Ex is this, but this is equals to what? It is Tx tau equals to minus x log tau, and U equals to 1/2. I know it's minus 1/2 of 2x logarithm tau. I think it is a nice way to see the kappa equation, and the whole hierarchy could be obtained the following way. We should write not a second order differential equation, but like infinite order differential equation, and do the same.
Well, it is, in some sense, it is dense of assumptions. You see, you have passed all this, like this follows one from another, but in fact, every equation is a result of some assumption, your construction. And
Oh, it's no, it's not some assumption. I just say that we have like solution of some second order differential equation, and now let all of parameters and function depend on two different all coefficients, and solution depend on two additional coefficients. And after that, the equation for the function remains the same, but equation for coefficients, it becomes something interesting. Like it looks like not a well, the compatibility conditions will give us the first proper equation. So.
Sorry, I don't
it
understand.
must be checked on every step. But another thing I want to say is this about positive hierarchy. KP has also negative hierarchy. So numbers going to the negative powers of.
In which way? I thought KP is just one increasing section of numbers. It's just every bn is just L to the power n. No, it's not the double to
you cannot use this formula you wrote in the beginning, the derivatives of A with respect to n's time is positive part of L to the n. It is different, but it has somewhere you had it. Where was it? Somewhere when you wrote a list of your promises.
Okay, I just wanted to tell that in definition of set the KP hierarchy is just how to say is generalization of this equation where okay, this W becomes pseudodifferential operator, and
well, Vadim, such approach is more than 50 years, I guess. No?
Yeah, probably, but I think it's I never saw it before, and I think it is an interesting way to look at this hierarchy this way.
Okay.
And could you show once more the place where you introduce additional parameters t and y?
This I just said that our equation now all coefficients depends.
Okay. So you said this, and you require that derivative over y is second derivative over x, and similar for derivative over t. Okay, so this is your requirement.
Yes, this is
for
my
solution, and this requirement, as I understand, it implies this partial differential equations for A and B.
Yes.
Okay, now I see. Because otherwise it would be strange, because you just say that A and B depend on two additional parameters, and suddenly you obtain some additional equations for them.
Yes, this is important.
That you require
But it's not very like hard equation. It could be imposed. It's just
okay. So now I see the point. This requirement on F implies some equations for A and B.
Yes.
By requirement itself follows from the, so to say.
Andrei, could you speak a bit loud? Andrei, Prof, I don't hear you.
Attacks, do you hear like
it's
this?
It's better. It's a bit better.
No, I want to say that this requirement, this with red color now, it follows from, so to say, standard approach to KP theory. It is not the way to derive KP. It is derived from KP as equation on, say, scattering data or whatever.
Okay. Okay. So may I continue to the whole KP hierarchy? As I said before, important for us also this equation for W operator and now KP. Let me say that any second order different operator is equal to d square, where v2 is equals 1 plus alpha 1 d minus plus alpha 2 d minus 2, and we determine like let me determine differential operators that such that g of f equals to fx and d minus 1 d equals to d minus 1 equals to 1. This definition allows us to just using the definition we can determine this object W2, and we could determine for example EG is something like G less than plus infinity, EJX DJ. This means that G for some n. This is a series, like we could call it pseudodifferential operator. It's like a different. The positive part it could be called a differential operator, and we have an operation. Okay, for example, we could multiply it. AD BD equals to AG less than infinity AE eta partial eta beta equals infinity, sum k equals to 0 to infinity, if k let me call it k. It's kth differential of b. So we could multiply this pseudo-differential operators. This is the just binomial coefficients. It is a plus 1, a plus k minus 1, k 1.
I'm not sure that this is binomial coefficient. E minus 1, E minus 2, and so on.
Let me, maybe it's wrong notation. It should be like, it should be k plus y, maybe.
In the upper line, k plus I. Yes.
K plus y.
Then oh, minus 1, I guess.
One. Let me just yes, it should be so minus 1. For 1 for k equals to 0, and it determined for all I like even negative ones. Yes. And we have operations such that a of t plus, which means just an taking positive part with 0, eg, dj, and non-negative, yes, equals just a of d minus a of the plus equals j strictly less than 0 ej gj. So this okay, and another we could for okay, for AG we have uniquely determined determined E of the inverse. To determine we should solve the triangular system of equation. I mean, yes, and we have also a of the dagger, which is equals to, well, let me start it. I d I a I equals minus 1 I 1 k e Okay. Well, it's just conjugation. It acts on a d minus GA this way, and it acting it acts on every term. Okay, so now we want to introduce something called well, it could be called the gauge operators. It's a pseudo-differential operators of following type: 1 plus g equals 1 to infinity. So it has just one in non-negative part and other and all other coefficients are negative ones, and this means that it depends on infinitely many parameters t1, t2, t3, etc. Where we at some point we could prove that dependence on t1 is the same as x, so we have something like dt1 dx. At some point, maybe I forgot it, but in order, if I will forget it, you should remember that sometimes x will appear, sometimes x won't appear, but it could be restored pretty easily from just notation with that. And we could introduce operators Bn. They are differential operators. And it is equals to power n minus 1 plus. And the equation which determined dependence of this Vj of t are following ones. It is Tn equals Bn V minus Vdn. And we could see that this equation look like what we have had here. Yes. But how to say? Here, W is differential operator, but what we could do if we this W corresponds to for example, it's W tidal such that let me just have such that W hat equals to W d square. Yes, I guess this gives us positive part. Okay, so this like system this is infinitely many system, infinitely many equation, and they are obtain the hierarchy. We could prove it's not so hard to prove that these equations are self-consistent. I mean that VTN TM equals VTM TN, but let me just introduce another important notation. It is L, it's a pseudo-differential operator, and it is equals to -1, such that, as we remember from our definition of Bn, so Bn becomes just Ln positive, and the equation for this equation can be rewritten in terms of equation for L is Tn equals plus with this notation, and that it is well known Lex operator, I guess, for Capet. Now let us introduce several important features. First of all, we have this omega, which is dependent on t. From this is operator. This is pseudo-differential operator, and we could construct a function pt as function of lambda such that equals to vt acts on xi t lambda. Okay, now what is xi t lambda? Xi t lambda, it's just infinite series. No, maybe just let me write it this way. This is the so recall that v of t as an operator, it was g, and here we replace. Now we could define W0 is 1. So just here, right? We replace partial derivative to lambda, and it would be, and we could. So what should we do? And we will define this psi of t lambda equals to wt lambda times t lambda, psi of t lambda, where xi t lambda is infinite series tn lambda n equals 1 to infinity. It's not well defined, but it is. We want from it to be just a formal series, and we could. Okay, we don't have. Let me write it this way. We don't know how g-1 acts on f. We don't know, but we could define the minus 1 acts on, for example, x lambda as x lambda minus lambda inverse. This definition is agreed with the main property that when we define on here applying d, we obtain lambda and it will become just 1. So we could define action of d minus on a very special function such as this. And from here we could see that using this definition, t lambda will be nothing, just a operator with t acting on t lambda. Okay. The same way we could define a joint function t lambda as of minus x t lambda. These two functions are important because they are so-called Becker-Heiser and adjoint Becker-Heiser function, because we could see that they are solution of linear problems such that L psi equals lambda psi and partial derivative and psi equals bn psi and psi joint equals psi adjoint and dt and psi adjoint equals to minus bn adjoint psi. Okay. This function is important, and now I want to prove the main theorem. OKP hierarchy is equivalent to okay, let me just write it this way. It first of all, it is equivalent to sorry, I need several more lemmas and definitions. Okay, before I want to formulate our theorem. First of all, let me introduce two types of residues. First, residue d of some function, some operator p. It is equal to p minus 1, where p is g less than infinity, pg dg. Okay, this is a very natural definition of residue. Now, the second residue is residue with respect to lambda, and it is of some series Q, for example, and it is just Q minus 1. It is, can you hear me? So, okay.
Yes.
Q equals to these are two very natural definition of residues. So, and I need one lemma to connect them, and this will be. See, I want.
Vadim, I don't understand your inequality. What is J is what?
It is G is lesser than infinity. It means that we have some integer n, so there exists n such that this sum are taken for all G is less than n. So it means just that we are how to say it, we have a ball.
Okay.
Okay, now of Z. Let me for the operators. Let me write down a head. Z. Okay, lambda. It should be lambda. Now Q minus x z equals to
Lambda.
Lambda. Yes, sorry. Equals to
and head probably for Q.
Yes, head for Q, and it is equals to rest of G P Q, and this could be obtained just from for simple calculation, and it is equal to something like in both of these cases Pn m such that n plus m equals to -1, something like that. P and Q, I mean, I think it's clear in notation that, okay. This is a very simple but a useful lemma. And now let me.
Something I don't understand.
What?
Where is the residue over lambda? Where is lambda to the -1?
I mean, on the left-hand side, the residue.
In the left-hand side, yes.
And what is? And here the residue in terms of operators. And
okay, but the residue of lambda.
Oh, okay.
Residue...
Sorry. Here we have. Here.
Okay, no, my question is not related to this. Correct. Yes. Where is 1 over lambda in the left-hand side?
On the left-hand side, we have here we have operator, for example, something like PND minus n acting on x.
Okay. Okay. Thank you.
You mean maybe it's a bad notation because we no, it's normal notation since after acting.
Okay, you produce negative powers of lambda when you act with p on exponent. Okay.
Yes. Equivalent to the following identity to being true for all indices E1, EM, and this one is res D1, E1, DM, DM, acting on psi adjoint equals to 0, this identity. Let me just so let me show that this one actually.
Once again, Z and lambda is the same.
Yeah, I don't write here. Yes, Z and lambda are the same. So if we have, what does it mean? It means if we have, first of all, if we have psi, which is Baker-Heiser function for keeping equation, that for all these multi-indices, this probably then when they all don't equal to 0, I mean, okay, for all these multi-indices, we have the following identity. On the other hand, if we have some, if we have such functions like psi equals xi t lambda sum n lambda n psi minus xi t lambda psi adjoint some like this series like that, we could construct an operator which will be a, from them we could construct operator W such that W will be just so W such that psi equals to W acting on xi t lambda. We could construct. Okay, this will define for us W, and from W we could construct operator N such that L equals V V inverse, and this L will be operator for KP. This is a theorem, and this is a very tricky. Well, it's not very clear how we could view this. It's a lot of notation, and it's in this like description, and it is more like interesting to view it the following way. We see that, for example, what is psi of T prime? It could be viewed as in terms of Taylor series. It could be viewed as a T prime minus T n D n kn factorial product over all n acting on psi t. So it this equality is just the same as write that this equality is the same as writing that residuals of lambda for psi of lambda t prime psi lambda t, sorry, here, yes, it's all right, equals to 0. And this could be written as an integral over some quantum near infinity psi lambda t prime psi lambda t equals to 0, which is a well-known, well, some form of well-known integral Hirota equation, bilinear. So I just wanted to say that this way to write it, it is useful for proof of this theorem, but it is not very useful into recognition of this. And in order to recognize it, the following, it is basically the same. I don't know. Is it clear? Or any question?
Yes, clear.
Okay. Now I want to prove this theorem.
Well, Vadim, it is clear, of course, but you, I don't know how to formulate this more exactly. In fact, it is impossible to use here terms like theorem or whatever, proof, because this is not a theorem. This is, in fact, condition.
Well, this is a theorem, no? This one,
No.
what I wrote in red, no? Why? Why it's not a theorem? It's well, it's two different just ways to describe it.
Vadim, you have to ask why it must be theorem, not why it is not theorem.
Why it is?
It is, you see, the problem starts from the very beginning here, in fact. So d minus 1z is not equal to 1. And after that, you got a lot of problems because you want to define not only d minus 1, but d minus n, n as large as possible. You understand that on every new number, you have new integrals of motion, which are integrals with respect to x or t1, but not integrals with respect to t2, t, and so on. So in fact, at every moment, you can add to your formulas arbitrary functions of t2, t3, and so on. Huh? How do you like such theorems?
No, I mean just this is a statement that if we have like two infinite series of such type as written down there, and here E all eta is positive.
Why do you think you have this? You see, you want to solve some fixed equation, Kp.
Yes.
Or let hierarchy P. So what do you know about properties? Why do you think that these coefficients or equation or functions, Baker-Heezer, functions, they obey these properties? Moreover, I know they do not obey, generally speaking. and it is hard to find relations such that this property is fulfilled. So to find, say, initial data for psi's or for, what was it, a by x derivative. The same, this theory, okay. So practically on every your line, I can protest. And I am not sure that you will find a way to prove something here. This is, okay, nice, very short presentation, but it is it's unclear what is it about, in a sense.
What it is about rewritten some equation. And for example, if we want to understand is this psi is Becker-Hazer function, yes, it has some finite like presentation. We could just try to check does this holds for.
Vadim, so first, it must be proved that such function exists. Yes. What do you call this Becker-Hazer function? It is uniquely defined. And so you have to prove that.
Well, it's not uniquely defined. We could multiply it for something from the right, I guess, because it's up to constant. Okay, up to constant, it's uniquely defined.
Okay, the same. This bilinear relation you wrote, the last one, yes, it is divergent. Integral with respect to t, integral about contour at infinity is.
Well, it's just notation. The integral, what is mean? It's defined here. It's a residue. It's and it could be proven that this residue is some finite sum. It because all our like series are have upper limit, for example, and because this is infinite series in one just one direction, we could easily we have a product for that.
But you have not said that you consider this as a finite, as a formal series. This integral at infinity, no?
Yes, maybe I should write this this equality here, but it is not in theorem. It could be saying that this equality is the way to understand this infinite, obviously converging integral. So this integral is.
Okay, but the same can be said directly about the theory, because you, first of all, you do not know if this psi's exist. Why do you know that you can write any condition and it is fulfilled? Why?
I don't know, but I said just that if psi exists and the Becker-Hazer function, they should satisfy this equation. And if some psi satisfied all this equation, they should be a Becker-Hazer function. I didn't say that they exist as a power series, but we know that KP Rahi had solutions such as the return solution.
Such what? Such what?
Like solid solution, I don't know.
Okay, solid solutions, yes, but so to say, if you have a solution on some generic background, no, then, the main problem will be about d-1.
Well, I don't know. I don't. This theorem is not for proving that we have some solution. So it's just a way to reformulate the hierarchy. Since from psi we could define this operator L. If we have some psi which satisfy this. So these equations, if we find that from this, we
permanently used terminology, we can define. No, you have to prove that you can define. This, what is characteristic for all this Japanese approach? They are introducing, in fact, dense set of definitions in every line. And it's rather hard to clear, to find the own conditions that are necessary and that you can apply. Yes, this gives some short presentation of known results in KP theory, but I don't know any results that is for KP theory that is obtained from this approach.
Well, I will say later that we had solutions which have a form of could be constructed from two matrices A, B, such that rank of the commutator is less or equal than 1. From this, we could construct our function. And for different choices of A and B, we could obtain soliton solution, we could obtain pole solutions. No, some well-known solutions for this system. And this theorem...
Few solutions, yes?
What?
Few solutions.
Few solutions, not all solutions. I don't say
you cannot
about...
say, yes, you cannot say what happens with solution if you start with initial data, say rapidly decaying on X, Y plane. You have no idea and no instruments for this. Okay?
Yes. Could I call them formal like solutions because I don't actually check in the like behavior on asymptotic, etc. Could I call them formal? So
yes, the problem is that in this approach you cannot do this. It's not the fact that you have not checked. You cannot do this. You need again some assumptions or whatever. Okay, well, this.
Okay, but it is easier, for example, for us to have like some pretend to check some I don't know something that could be a solution to check its behavior on asymptotic, etc., and says that it is a solution that don't have anything, so it is not useless. Because it is some necessary condition for solutions. Like we could know that something that solves this at least could be a solution. And in order to obtain it, is it a meaningful solution? We should just more like, well, look at it more intense. I don't know. So it's I don't see any problem. I don't see say that
what you derive from here looks like a solution, but in fact I would check directly every such statement.
Okay.
To check with explicit solution. Yes.
Okay, it's a solution in some algebraic sense, yes? It's not solutions like in
Vadim, there is only one
okay.
solution of equation. Left-hand side is equal to 0. No, there is no algebraic sense of solution or whatever.
Okay. Let me just continue to prove this theorem. I just wanted to say that this theorem has a statement in both sides. First, that if we have psi which solves this equation, from them we could construct a L operator, and I probably won't prove it, but I think Masha here, yes, Maria proved it about a half of a year ago on one of a seminar, and it could be viewed in YouTube. And I want to prove is that if psi and psi adjoint are Becker-Hazer function and adjoint Becker-Hazer function, then they are solution to this. So I just prove the theorem in one way. Okay, and in order to do this, let me just start here. Psi star Becker-Hazer functions. Now, after that, we want to show that lambda. Now I just want to d1, u1, dn, en, psi star equals to 0. Now, it is clear that it is sufficient to prove if only for d1, which is just d, into some power n. Because we have, since psi is Becker-Hazer function, then dn psi is equal to bn psi, which could be viewed as with some coefficients dk b nk dk psi. So if we had like this multi-index contains some I which is not equals which like d2 or d3, we could from it obtain this. If we prove it for dn psi psi star, then for d3, for example, psi, it will be will be just consequence because we have a linear combination of such term, so it's not necessary to prove. So we need to prove it only for lambda psi star. Okay, now let us recall the definition. It is less dn psi is our omega, which is operator, and it's acting on psi of lambda, and this will be omega, sorry, not omega, W minus E C minus and of lambda. And here let me use our lemma. Using our lemma, we have that it is dn. Since conjugation and inverse are commutative operation, we have this just -1, which is dn, which is equal to 0. Okay, so we have proven our theorem in one way. Another way, it is a bit more difficult, but it is it was proven, and I already said we could find this proof. Now I don't have a lot of time, so let me just say that it can be proven that this psi lambda t psi lambda t lambda infinity, this integral, which is in some formal, we understand it in some formal sense, equal is the whole copierarchy. Now it could be proven that psi lambda t, sorry, here we have, is equal to t lambda some functions t minus lambda t star lambda t equals x t lambda. Let me say the notation. Lambda t as
of lambda.
And lambda, and here we have lambda minus. It is a vector such that it has a component 1 over lambda, 1 over the 1 over third, and the third, etc. So it is this infinite shift of times. Probably, I don't know, should I prove it or should not? Should okay, let me prove some of it. Let me prove. Let's call this part of lambda t, and let me prove that. Let me prove that v t lambda equals to this will be v star lambda t. Sorry. Lambda t minus lambda minus 1 equals to 0. Sorry, times equals to 1. Sorry, equals to 1. Let me prove it. As we could see from this definition, it is clear that it should be so, because after the shifting, this became just inverse. this equation. Just if we shift lambda this way, this equation here will be just t, here will be t plus this shift, and this expression will be inverse of each other. But we want to obtain this from our equation, let me see, t minus t lambda omega lambda t omega lambda t equals t lambda. Let us obtain this from this equation. We set here t prime equals to let it be t minus z into one side shift, and after that we will use that yeah of c this minus 1 lambda is equal to a x but some lambda k, oh sorry, lambda to the power k zeta k, which is equal to x at logarithm of 1 minus lambda zeta. Probably I should have here something like minus, maybe I should have here plus, minus, and put it 1 minus the 0. This is a very important trick, which we will use later for our proofs, and so this like shifts are related to okay, this operation. Let me just check, is it everything all right? Okay, and now this equation after t equals to probably the problem I have, it should be this one. So plus, sorry, minus, and no, okay, so I just wanted to say that it should be equal to infinity d lambda v v of t v star t minus zeta minus 1 1 minus lambda zeta equals to 0. Now it could be shown sorry, here we have alpha. It could be shown that this integral is equal to okay, its integral is equal to zeta we w t minus plus z minus 1, and it should be equal to 0. This is because we just it should be true for all f over lambda such integrals where f of lambda equals 1 plus plus some negative powers of lambda minus 1, etc. It should be equals zeta f of zeta minus 1. Because we could we take here residue, and this is the same what, okay, maybe the wrong sign here, what we wanted to prove. So what should be? So maybe I had a right sign on the right. Okay, this is the same we have. No. This is just. This is what I wanted to prove, and to prove that there exists such a tau function that we could write psi and psi star this way. We should do something like this, just more complicated, and probably I should stop. And after that, I just wanted to tell that there is another equation which results from from this integral equation, and this equation could be, let me just announce, Hirota equation. It could be some equation could be written the way lambda 2 lambda 3 tau t minus lambda 1 tau t minus lambda 2 minus lambda 3 inverse plus cycle equals to 0. This equation could be easily obtained from integral 1 if we from this integral equation if we use the same shifts. If we take t prime as t with some shifts like that. But it is also an interesting result that this is equation are itself like the same as this integral Hirota equation, and it could be proven like in both sides. And we will use this equation to prove that we have a solution from almost intervenient matrices. But it will be the next time, I guess. Any question for today?
Okay, I need a couple of minutes to formulate home task for the next time for everybody. Okay, do you give me a couple of minutes?
We give you a couple of minutes, but the task for everybody we don't give you.
Okay, for those who want. So Vadim, I need your assistance. Please write
Yes.
KP equation. Write down.
I don't remember. UT minus 6 UX minus UXXX, something like.
Okay, yes. One more derivative in X. So now you like, as you like, d minus 1. Okay? Please apply d minus 1 from both sides to this equation. I want you to have equation as evolution with respect to t.
What do you mean d minus 1 is a formal operator. I don't we don't have an action of d minus 1 on a function. We don't know how it acts.
But how to find the equation for u? I want to have equation to solve initial problems. I need to know u by t derivative, no? Given by some value of u at t equal to 0. So I need to find the u by t.
Well, I don't understand. Why do I need G inverse? Why do I need d minus 1 in this situation? I don't understand. I just
to have okay, just write integral with respect to x. No?
You mean dx of
remove this d minus 1 and
okay, so it will be something like that. Sorry, y dx equal to, I don't know, from a to b, for example, x minus x.
Okay, then what is low limit?
For example, 0.
Why? Why do you know? What
well,
is
I don't.
What is b at the top, and what is? No, it is integral with respect to x. So integral from 0 to x or forever. But you have to understand that if you change this 0, then you have another equation.
Yes, I understand it.
So what equation are you studying? What is and this is not a constant, because integral with respect to x is function of y and t.
Well, so I study. I have some. I have infinitely many functions. So they are coded as a coefficients of this operator. Something like.
Okay. Why do you speak about infinity? I understand it is easier to make problems speaking to infinity, but you are we're speaking about lowest equation, KP equation. This is KP equation.
Yes.
How to understand it? What is written? First of all, it must be explained. What is written here?
Well, it's just some fourth order equation in partial derivative. I need some initial condition or something like that to solve it.
I choose condition. U decays rapidly enough on initial data. Decays rapidly enough. This function on x, y plane. So what? You understand? You have some explicit value 0, and you want to, I don't know, to do something.
I have some solution. I don't know, like a common solution for initial problem, but I know there's some function which solve this equation. And what I'm talking about is some function which solves this equation. I don't like set some boundary conditions and something like that, because it's not my task. My task is to construct some functions that, for example, we have here solitons.
So, okay, solitons. So what is the left-hand side for solitons? Left-hand side, I mean, in this second equation, which wrote by some reason from 0 to b, which I don't understand. You have problems
from a to b or from minus infinity. From solitons, I don't remember. I don't recall a formula for solitons in KP. But for example, we could what could we do? We could take this integral from. Well, this will be some function of a and b and parameters of solitons. Yeah, I don't.
But the function in the left-hand side cannot depend on the choice of this 0 or whatever, a.
Why?
Yes, because it is. It has no a and b in its definition. Remember formula for a one soliton solution?
I don't recall.
Andrei, I also don't understand. Okay, the function u does not depend on a and b. When we integrate from a to b, the left-hand side depends on a and b. What's the problem?
And the right-hand side doesn't depend.
It depends because it has a. We take here like ut at the point A minus ut at the point B, for example. It does depend on A and B explicitly.
Okay. Okay. You've chosen A, but move this value at A to the left-hand side. That is, you have constant there, so this is also constant. And B is X. Why put some B?
Okay.
Take away this constant to the left-hand side. It is just change of A. So what? It is equation. It has some value. The same will be with tau function.
Yes, and I understand. I don't understand what's the problem with this. That I don't.
The problem is
what a contradiction with something I told before, because I have like something infinitely many functions or what, or I don't have some point. We could define this operator. It depends on infinitely many times, but we could set all but 2 or 3 times to.
In your terms, I guess the bad idea is to say that we have no definition of d minus 1. Then you can do whatever you want, of course, but this not strict. It's not strict correct mathematics.
Well, but we don't have d minus 1 in the answers. We like d minus 1 is just maybe some way to, I don't know how to say it. It is some way to work with our infinite series because we don't have in final answers we don't have something which depends on d minus 1. We want some like properties of this operator, and I don't know, probably we could.
This example, well, I just suggest you a simple example where you have d minus 1.
But it was in what I told before. We don't define action of d minus 1 and at some function. I recall that I specifically said that the d minus 1 doesn't act on a function. Let me recall this. Here I said that we don't know what it is, and it probably doesn't define that. We have a definition that it how it acts on this.
Okay, that's because you work with soliton solutions or whatever. You don't want to use this for generic solutions. Okay, well, too late and maybe everybody too tired, but okay, think about this. Maybe you will find some solution.
Okay.
Yeah. Okay. Sorry for such a long lecture. Okay. Ciao.
Okay.
All the best.
Yes. Maybe anybody have other question? I could answer them.
I think we can postpone all questions to your next lecture.
Okay. Okay. Thank you.